Okay, now we'll see all the phases in iron carbon diagram. Okay, first we will see from the above delta ferrite. Delta is known as it is an interstitial solution of carbon in BCC alpha ion. Okay, now when we say BCC, we know that iron is having the allotropic nature, and delta is nothing but it is a ferrite. Now when we see the delta, the maximum carbon in delta is 0.1 at this temperature 1492, and this reduces to 0 at 1539 and 1400. So in between this, the phase which is there, which is known as delta phase. Now delta ferrite and alpha ferrite, are they different? Yes, the difference is only that delta is existing at higher temperature and alpha is existing at lower temperature. Both the phases, they are not stable. Delta is not stable, alpha is stable at room temperature. So in the structure you can see the alpha, but you can't see the delta, because delta on cooling is transforming to austenite by the photolytic reaction with the liquid, and then austenite decomposes into alpha plus cementite. So at room temperature you can see the alpha, but you can't see the delta. In both the delta and alpha, the carbon is so less that this ferrite phase is so soft, and the softness will change with the change in carbon that we have seen early. Okay, so higher the carbon, higher is the hardness, lower the carbon, lower is the hardness. That is what. Okay, now we can see the delta phase. This is known as interstitial solution of carbon in BCC delta ion. Only in alpha and delta, that is the main change in delta ion. Okay, now the structure of delta ion is something like this. So delta is having the BCC structure. Now delta is changing by reaction to the liquid to gamma austenite. So gamma austenite is known as interstitial solution of carbon in FCC crystal structure. Now you can see the difference, that the crystal structure which is existing here is FCC crystal structure, right? So FCC crystal structure means the crystal structure which is existing here is a FCC one. Now being FCC one, this is more ductile, rather than having the more percentage of carbon. At 1147, that is at its point, the solubility of carbon is more than delta, right? But why this is more ductile? Because it is having the FCC crystal structure. Now the crystal structure will change the number of slip system in the crystal structure, and this will change your ductility. So being FCC in crystal structure, this is having more ductile nature in the all the iron carbon. So this is the region where you can see the delta ion which is present. Okay, so in this region the delta ion is present. Maximum solubility is this, and minimum goes to 0. At 727, that is at eutectoid point, the solubility of the carbon in austenite is 0.8. Austenite is a metastable structure. What do you mean by metastable structure? Metastable structure is a structure which is not stable, below any certain point, and that point is known as eutectoid line. So below eutectoid, you can see austenite here, you can see austenite here, you can see austenite here, but you can't see anywhere the austenite. For getting the austenite at room temperature, you need to have certain alloying elements which are austenite stabilizer, which stabilizes the austenite at room temperature. But currently we are talking about the plain carbon steel, so we are not concentrating, or we are not doing any calculation of the alloy steel. Okay, so that part comes in the alloy steel. Now austenite will decompose. This is a metastable structure, and this decomposes into alpha plus cementite. Okay, now this alpha plus cementite is nothing but this is known as perlite. Perlite is also known as mechanical mixture of alpha plus cementite. Now what is difference in mechanical mixture and a chemical mixture? Mechanical means they are mechanically mixed together, but individually they are having the individual mechanical variation or the mechanical properties of the material. Okay, so alpha will behave like a soft and cementite will behave like a hard cementite. But as they are together, cementite lamellae is so thin in nature that you can have the change in the hardness when the cementite percentage is changing. Okay, cementite and ferrite you can do the calculation by the lever rule. So as per the lever rule, according to lever rule, at room temperature, what is the percentage of alpha and what is the percentage of cementite will change its hardness. More is the alpha, more is the softness, more is the cementite, more is the hardness. Right? Now, we'll see that the interlamellar distance in the perlite can be changed by changing the cooling rate. So, what transformation we are getting by the austenite? We can change austenite is a metastable phase and we can change by cooling rate the transformation of austenite. More is or faster is the cooling rate, lesser is the interlamellar distance. Lesser is the interlamellar distance, better are the mechanical properties of the material. Right? Now, based on the perlite can be resolved or unresolved perlite. Resolved means interlamellar spacing, the lamellar spacing in between the austenite, in the ferrite and cementite is more. Coarse is the perlite. Lesser is the distance in between cementite and ferrite. Finer is the perlite. Finer is the perlite. You can see the mechanical properties are better. Which mechanical properties? Like the hardness, strength, they are better. That is what we are doing in the heat treatment. Okay, by changing the cooling rate, we are changing the transformation. By changing the transformation, we are getting the change in the mechanical property of the material. We will see in the heat treatment. Okay, now what do you mean by Fe3C? Fe3C is also known as, it is a cementite and it is an intermetallic compound. All the intermetallic compounds, one thing is common, that they are hard in nature and all of them they are having the higher melting point, right? That's why you can see that in tool steel, all the compounds, they are the intermetallic compounds. Now what do you mean by intermetallic compound? When the two metals are added into each other, they can form either interstitial or substitutional solution, or the third one is an intermetallic compound, right? When the intermetallic compounds are formed, the structure is hard in nature. So this is having the fixed percentage of carbon, that is 6.67%. Okay, that is what is a cementite. Now cementite, is it stable or not? Yes, this is stable at room temperature. Austenite decomposes into alpha, that is ferrite, plus Fe3C, that is cementite at room temperature. So you can see the cementite here. Okay, so cementite is present and this mechanical mixture is known as, at room temperature, it is known as perlite. It is a mechanical mixture of ferrite plus cementite which is transferred by eutectoid reaction at 727 and it appears in the, what is said, lamellar form, means line-like form. If the cooling form austenite region is very fast, it leads to the fine perlite and better mechanical properties. What we discussed earlier is the same. Now, what is this structure? This structure are the perlite only, but you can see the coarse perlite here and you can see the finer pearlite here. Here interlamellar spacing is more, so deteriorate are the mechanical properties and better are the mechanical properties in the second structure. Now, what do you mean by ladurite? Ladurite is nothing but it is a mechanical mixture of cementite plus austenite, which is transferred by eutectoid reaction at 727, and this chemical mixture we are getting by the eutectic reaction. We see again by the in the ion carbon diagram. Okay, this mechanical mixture of austenite plus cementite in between the 727 and 1147, this mechanical mixture is known as ladurite. Now, ladurite in these two, austenite plus cementite. Austenite is what? Beta stable structure. So, austenite again decompose it into alpha plus cementite, and that is why this transfer or the mechanical mixture of these two, which is transformed by the eutectoid reaction, is known as transformed ladurite. And you can see the mixture. So everywhere you can see the mixture of alpha plus Fe3C.